Hello there. So this is the second video of section 1.2. In this video, we're going to now present the algorithm for calculating the reduced row echelon form of a matrix. I might have talked about that or sort of thrown around that definition last video without formally defining it, so I wanted to make sure this video I do define it. So we say that if a matrix A is row equivalent, and so remember this term row equivalent means that I can start with A, perform a sequence of elementary row operations that we introduced in section 1.1, and get to a matrix U. So if A is row equivalent to U, and U is in row echelon form, so remember that's the weaker version where it only has the first three properties and not all five, then we would say that U is n echelon form of A. And if U is an RREF matrix, that is a reduced row echelon form matrix, then U is the reduced echelon form of A. So notice a key difference here in two words. When U is an REF matrix and when U is an RREF matrix. So if U is just in reduced echelon form, or row echelon form, sorry, excuse me, U is n echelon form matrix, that means that there are many different echelon form matrices that are row equivalent to a matrix A. That is, when I perform a sequence of row operations on a matrix, I might get a set of different row echelon form matrices that are row equivalent to A. But notice, and we introduced this as a theorem in the last video, if U is in reduced row echelon form, then U is the reduced echelon form of A. That means that the RREF matrix that is row equivalent to any matrix A, which again we talked about at the end of last video, is unique. And so in fact, what we're going to do today is we're going to present the series of row operations that we can use to turn this matrix A into its unique reduced row echelon form matrix U, which is given here. So first things first, we're going to be using this definition a lot throughout this chapter, but also throughout the entire semester. A pivot position, or sometimes just referred to as a pivot, in a matrix and so sometimes we'll just call this a pivot, in a matrix A is a column, or sorry, pivot position in a matrix A is an entry in A that corresponds to a leading one in the RREF of A. So a pivot position is an entry in the original matrix A that corresponds to a leading one in the RREF, or reduced echelon form of A. A pivot column is just a column that contains a pivot. And so we will refer to pivots and pivot columns quite frequently throughout this course. So the reason I'm giving you, at least right now, the reason I'm giving you matrix A and its reduced echelon form U is so that we can really sort of see exactly what pivots are. So notice here, the leading ones in this matrix U are this one here and this one here, right? So there are no more leading ones, right? There are no more, we've got two rows, right? We've circled the leading ones in each of those two rows. This last row is on all 0 rows, so we don't even really have to worry about it. So these leading ones aren't the pivots. The pivots in A would be this one and this 5, right? So like it's the sort of, you can think of the pivots as the spots in A that are eventually going to turn into leading ones after we perform our sequence of row operations. And so we'll show how that works, of course, in the algorithm. But when we talk about pivots, we're talking about these entries in A that eventually become leading ones in U. So the ones themselves aren't pivots, it's the entries in A that are the pivots. And so here, pivot columns in A would be columns 1 and 2 because those are the columns that contain pivots. And so basically the way that this algorithm is going to work, I'll give sort of a brief overview, is, right, so remember a matrix is in reduced row echelon form. If every time we have a leading one, all of its other entries in the columns, right, are zeros. So the leading one should be able to look up and down and see only zeros. Now, basically what we're going to do, remember we have these row operations that allow us to take scalar or constant multiples, of rows and add those sort of rows to other rows. And this allows us to change the entries in other rows of the matrix. And so basically what we're going to do is we're going to identify these positions in A that we want to be pivots, or that we want to eventually turn into leading ones, and use those pivot positions to sort of zero out all of the other entries in the columns, right? So you can kind of maybe already see what's going to happen in column 1 here. Eventually we want column 1 to turn into a column with a single 1 at the top and 2 zeros below it. And so we can actually use row operations and use this 1 to just eliminate this 4 and this 6. And so the algorithm, basically, we're going to find these positions we want to be pivots, use them to clear everything else out, and do that until there aren't any pivots left. But we will do it a little more formally than that right now. All right, so I will probably need the whole board to do this. So keep track on some piece of paper you've got, write down A and write down U, so you know what we're working towards. We're working towards this matrix U, and we're going to start with this matrix A. And so I will row reduce this matrix and give the steps that you can use to row reduce any matrix at the same time. So we'll call this the RREF algorithm. And here's our starting matrix A. 1, 2, 3, 4, 4, 5, 6, 7. 1, 2, 3, 4, 4, 5, 6, 7, 6, 7, 8, 9. All right. So step 1 in our algorithm, you want to circle the leftmost non-zero column, or we'll say, rather than circle, identify the leftmost non-zero column. And so in this case, notice it's column 1. In this matrix, A is the leftmost non-zero column. What you want to do is pick any entry to be the pivot. And so this is actually sort of a key distinction here, which we won't see matter too much in this process, but can be very, very useful to you while you're row reducing your own matrices. We can pick any entry to be the pivot, meaning I can pick either this 1, this 4, or this 6 to eventually become the leading one in the reduced row echelon form U. And all I have to do, right, is whichever one of these entries I want to pick to become my pivot, I just sort of swap it into the place that it's eventually going to be in U. Right? In this case, I'm going to pick this 1 to be my pivot because, as you'll see, and what I'll say now, always pick a 1 if the column contains a 1. So I'm going to pick the 1 to be the pivot. And so this step won't really matter here, but if necessary, swap rows to put it in the correct position. So remember, a reduced row echelon form matrix has some key qualities. Right, I've got leading ones in every non-zero column that are to the left of leading ones before it. And so what we're going to do when I say put it in the correct position, you want it to be as far to the left as possible. Like if thinking about going left to right, you want whatever pivot we've picked to be as far to the left as possible and as high up as possible, while still not violating the RREF restriction. So in this case, the 1 is in the exact correct position, right? That 1 is eventually going to turn into a leading 1 as far left and as far up as possible. So this first step, a lot of this doesn't quite matter too much yet. We'll see with the second step where all of this will start to matter. All right. Step 2, and actually you have an option here in step 1, which again will matter a little more in a second. You can actually scale the entry to just equal 1 immediately. What I mean by this, eventually the entry is going to turn into a 1 because that's what we eventually want with our reduced row echelon form matrix. Sometimes it's useful to do that, sometimes it's not. We will see again with step 2 actually is where most of this starts to matter more. Or sorry, not step 2, but later on in this process, it'll start to matter more. So there's step 1, by far the longest step. Step 2, you want to zero out each entry below the pivot using row operations. So now we get to really do some row operations. So zero out each entry below the pivot. So this means I want to use row operations to zero out each entry below the pivot. So first I want to turn this 4 in row 2 into a 0. So I should do negative 4, row 1, plus row 2. And this should replace row 2. And again, so this means negative 4 plus row 1, negative 4 times row 1 plus row 2 in order to replace row 2. And this should give me the matrix 1, 2, 3, 4, 0, negative 3, negative 6, negative 9, and 6, 7, 8, 9. And we have one more entry below this chosen pivot 1, which is the 6. And so in order to zero out the 6, I'm going to do negative 6, row 1, plus row 3. And that will replace row 3. And so this gets me the matrix 1, 2, 3, 4, 0, negative 3, negative 6, negative 9, and 0, negative 5, negative 10, negative 15. All right, so as you might notice if you're looking at the eventual RREF matrix U while we're doing this, so notice that like this first column now looks exactly what we want it to look like once we get to the RREF matrix U. So what we're going to do next is sort of kind of ignore column 1 and move our way down and to the left. And so I realized I'm going to need a little more space here for these steps. So step 3 is move, sorry, not down and left, move down and right. And repeat steps 1 and 2. So what does this mean? We want to move down and right, meaning we want to ignore column 1 and ignore row 1 for now. Looking at then the remaining rows and columns, we want to pick our next potential pivot position. And we want to do exactly what we just did. We want to zero out all of the column below it. We want to turn it into a 1 if necessary. And we want to put it in its correct position. So in this case, you could choose, so notice now, I'm ignoring column 1, ignoring row 1. I want to pick now the next possible entry, right? So I want to look for the leftmost non-zero column. This is column 2 now because I'm ignoring column 1. Pick any entry to be the pivot. Well, I can't pick the 2 because I'm also ignoring row 1, so I have between -3 and -5. It actually doesn't matter which one you pick. Just for the fun of it, so we can see the full power of step 1, I will pick -5 to be my next pivot position. So 5 will be my next pivot entry. And we're going to now repeat steps 1 and 2. So step 1 tells me, because I've picked 5, I should perform a row swap to put it in the eventual pivot position it will be in. And so remember, that should be as far up and as far left as possible while not conflicting with any other pivots. And if you remember looking at the row echelon form U, or RREF matrix U, this was exactly where I'm putting it now. All right, so I've swapped rows 1 and 2 so that 5 can find its way to its eventual resting spot when we get to the RREF matrix. Next, notice I have the option I can scale the entry to equal 1. I'm actually going to do that now. And so this involves multiplying -1/5 times row 2 to get the following matrix. Specifically, what I'm doing here is I'm turning this 5 into a I'm turning this 5 into a 1 because eventually we do want that position to be a 1, right? Because this is corresponding to a pivot position. I do this for a couple reasons. One of the reasons is that it actually does make the process of zeroing out the entries below it easier. That is because generally 1s are just easier to work with than any other number. So I'm complete with step 1. I've got my pivot position in the correct spot. I've turned it into a 1. Now I want to zero out each entry below the pivot. So there's one entry below the pivot, right, which is -3. That is, the 1 should be able to look down and see only zeros. So I'm going to do 3 row 2 plus row 3, and that will replace row 3. And notice here, 1 plus 3, or 3 plus 3, -3 is 0. 2 times 3 is 6, plus -6 is 0. 3 times 3 is 9, plus -9 is 0. And so I've sort of conveniently turned this bottom row into just a row of all zeros. And so at this point, actually, we're almost done. So identify the leftmost non-zero column. Remember, if I'm going back to step 1 now, right, I have to move down into the right, repeat 1 and 2. I also have to ignore, maybe I'll put this as an official step here, ignore current pivot columns. So now, okay, I've made 1 into a pivot column, I've made 2 into a pivot column. I need to move down into the right and identify the leftmost non-zero column. But if I'm ignoring rows 1 and 2 and columns 1 and 2, if you notice, I'm left with just zeros. And so the second I can't find any other non-zero entry to be a pivot, I'm done with steps 1 through 3, and I move on to my final step, step 4. And so the last step, step 4, tells me to zero out all columns containing a pivot. And if necessary, necessary scale to get leading ones. All right, so once I have identified all possible pivots, and there are no more possible columns that could be pivots, I want to zero out all of the columns containing a pivot. Remember, in the RREF form of a matrix, the leading ones should not only be able to look up, but they should not only be able to look down, they should also be able to look up and only see zeros. So really all I have left to do for this matrix is make sure that this second leading one here looks up and only sees zeros. So this will be -2 row 2 plus row 1 and replace row 1. And so notice that will get me the matrix 1, 0, -1, -2, 0, 1, 2, 3, 0, 0, 0, 0. And so, using the RREF algorithm, I have worked my way, started with A, row reduced A down to the RREF form U, and we are done. All right, so next video, we will do this process again. I highly recommend just finding random matrices and practicing sort of working these down. If you Google search RREF calculator, there's actually, I think, many great websites. I think it's like the first or second one, and it's like an edu address, which is one I always use to check my RREF work, because this tends to get, well, there's a lot of addition and multiplication and subtraction, and surely at some point this year you will see me make a silly arithmetic mistake. And so I would highly recommend, there's a great website, maybe I'll put its link in Canvas actually, that will calculate an RREF for you and show you all of the intermediate steps. And so I would highly recommend that, like just picking a random matrix, opening your book or opening any linear algebra book, finding a matrix, trying to put it in its RREF, and then typing this matrix into any RREF calculator and sort of checking your work, just to get the practice with doing this. I've found this algorithm to be very, very, I think I remember it was pretty confusing to me at first, but it starts to become much more natural the more you do it. So any questions, like I said, send an email, and thanks for watching.